I've had a few questions on how to calculate the ANOVA associated with the APA results section. So what I've done is I've drafted up a set of data that looks similar to what you have. You have a mean, you have three groups. Each one you're given the mean, a sample size, and the sum of squares. We've got big N over here. That is the total number of participants. So N1 plus N2 plus N3. So what this is 10 plus 10 plus 10. Big G is the sum of all of the scores in treatment 1 plus all of the scores in treatment 2 plus all of the scores in treatment 3. You're not actually given those scores, which is fine. You don't need the raw data to calculate this through if you have the hand calculations. And then this is the sum of x squared. This is each of those x values squared and then added up. So the first step of the hypothesis testing procedure is our hypotheses. The null is that the groups are all the same, that group 1 equals group 2 equals group 3, and the alternative is at least one group mean differs. What the ANOVA is doing is it's comparing group 1 to group 2, group 1 to group 3, and group 2 to group 3 all at once without increasing our overall alpha level. If we had conducted those comparisons as t-tests right out of the gate, then our alpha level would not stay at 0.05, which is where we want to keep it. If we get a significant F statistic, all that we're going to be able to conclude is that at least one of these groups is different from the rest. All of those comparisons could be significant. We wouldn't know until after we calculate post hoc tests, and those would only be calculated if we have a significant overall ANOVA. Step 2, we need our critical value. To find our critical value, what we need are some degrees of freedom. And so we're going to go to table B4, because that is the table that is used for the F distribution. And what you see here is you have degrees of freedom numerator, degrees of freedom denominator. What that's referring to is, I'm just going to flip this over so I have a bit more space. The F statistic is calculated by taking mean square between divided by mean square within. Mean square between is calculated by taking sum of squares between divided by degrees of freedom between, and then mean square within is sum of squares within divided by degrees of freedom within. So when the table says degrees of freedom numerator, it's talking about degrees of freedom between. And when it's talking about degrees of freedom denominator, it's referring to these degrees of freedom within. So we need to calculate those. And we have formulas for each one. The degrees of freedom between is k minus 1, where k is the number of groups we have. We have 3 groups, so 3 minus 1, and that's 2. And we need degrees of freedom within. The formula for that is big N minus k, where big N is 30, minus k is 3. So that's 27. So we take those two values over to table B4, and we look down until we find 27, because that's our degrees of freedom within. And we look over degrees of freedom numerator. That was our degrees of freedom between, and that was 2. So we're going to come down here. And in light-faced font, is alpha is 0.05 and bold is alpha is 0.01. So our critical value is 3.35. Critical value. If distribution looks a little bit like this. And so n, if this is 3.35, anything that falls out here is going to be reject the null, accept the alternate, and anything that's over here is going to be fail to reject the null. What we need to do now is calculate that F statistic. So that's step 3. And I like to organize everything into an ANOVA summary table. In the ANOVA summary table, you've got the first column is source. And it has underneath it in the following order: between, within, and total. The next column over is sum of squares. And we will put, when we calculate it, we will put sum of squares between, sum of squares within, sum of squares total. We have degrees of freedom. We're going to have degrees of freedom between, degrees of freedom within, degrees of freedom total. We're going to have mean square within, mean square between, mean square within. And I'm running out of space, so I'll put it down here. We also have our F statistic, which is mean square between divided by mean square within. We have some values already calculated, so I'm going to pull those over. The degrees of freedom between was 2, and degrees of freedom within was 27. And move this here. The next we can calculate, well, we can calculate some sum of squares, but we might as well finish this degrees of freedom. We have a couple of formulas that we can use. I'm going to use the relationship formula, which is degrees of freedom total is equal to degrees of freedom between plus degrees of freedom within. So that's 2 plus 27, which is 29. And yes, you really should be showing this much work, especially on an exam. I'm going to then calculate sum of squares within. I could do sum of squares within or sum of squares total, equally easy at this point. So within is sum of squares 1 plus sum of squares 2 plus sum of squares 3. And if I had more groups, I'd keep adding. So that's 118 plus 134 plus 142. I've got 394. And that's not total, that's within. Sum of squares total is sum of x squared subtract g squared divided by big N. Sum of x squared was 225,914. Subtract g is 2600 squared, right? Divided by big N, which is 30. 225,914. So 2600 squared is 6,760,000 divided by 30. And divided by 30 is 225,333, and 3 repeating. And so 225. And I know that this number has to be less than this because this is a sum of squares. Sum of squares are sum of squared deviation scores. Anytime you square something, it's going to be positive. So I know that this sum of squares needs to be positive. And in order for this to be positive, this number that I'm subtracting has to be smaller than this number. I get 580.67. To get sum of squares between, I'm going to take sum of squares total, subtract sum of squares within. So 580.67 subtract 394. I get 186.67. Now I can calculate my mean square. Mean square between, sum of squares between, divided by degrees of freedom between. So 186.67 divided by 2. $93.34. Mean square within is 394 divided by 27, because it's the sum of squares within divided by degrees of freedom within. So 394 divided by 27. 14.59. Running out of space here. I'll do my conclusions on the back. The F is mean square between divided by mean square within. Mean square between was 93.34 divided by 14.59. $6.40. So that's the value that I'm going to compare to my critical value. So my critical value, just I'm gonna go back here because I need space. Critical value was, what was it? 3.35. My F calculated that, so this is step 2. This is what I just calculated in step 3, is 6.4. Because what I calculated is bigger than my critical value, I'm going to reject the null, accept the alternate. That's my decision. My evidence, so that I'm not pulling it out of my ass, my arse, right? 6.40 is greater than 3.35. And to conclude, at least one treatment differs from the others. Which one? I don't know. I have to do post hocs if I want to make that conclusion. The last piece that you'll have to do for the for a lot of calculations is eta squared. That's your effect size measure. And that is calculated sum of squares between divided by sum of squares total. Sum of squares between is 186.67. Sum of squares total was 580.67. That's 0.32. That's a large effect. That's a large effect. Anything above 0.14 is a large effect. I guess the last piece to mention is if you were writing this up in an ANOVA or in an APA results section, what you would do, you would have your statistics and you'd have your P, and if it's statistically significant, less than 0.05. Or if you had used 0.01 to get your critical value from your table, then that's what you would put in. If it was not statistically significant, so if the calculated value was smaller than the critical value, then P would be greater than 0.05. But there's no way to calculate a p-value with more decimals unless you're using software. So this is what I'm expecting. This is what I want to be seeing on anywhere that you're not supposed to be using computer software. And computer software includes software that could be in a calculator. All right. So that's your full ANOVA.